This is example problem 5.3, calculating the pH of a weak acid. So one thing to look out for in this kind of problem is that it usually won't actually tell you that you're working with a weak acid. But you only have like a few options of kinds of problems that you know how to solve. So chances are good that it's either a weak acid, a weak base, or a salt problem. And how do you even know if it's a weak acid versus a strong acid? Check your list. Before you start working on the problem, think about what it's asking. So to find the pH, you're going to have to eventually find the concentration of H+, and then go from there. So let's move all of this up. As always, the first thing we're going to want to do is to write out our equations. So our first one is going to be the addition of our weak acid to water. Remember your generic equation for this. Remember, when you dissolve a weak acid in water, the principal species that is produced is hydronium ion. And that takes the water plus the hydrogen, the proton over here, out of solution is H3O+, and the thing that is left over is the NO2, which is now going to be NO2- since you took a proton away. The other reaction that is always happening is the autoionization of water, so never forget to write that out in these kinds of problems. All right, let's assign our variables. HNO2 can be X. Water, liquid, we ignore. H3O plus is P, and O2- can be Y. Water we ignore. H3O plus again is P, and OH- is H. Those are all the equations that describe what is happening in solution. So now we're ready to define our inputs, equations, and outputs. From the problem, we know that the concentration of Xi is equal to 0.25. We assume that Yi is equal to 0, and as a special note, for acid-base problems, we are never, ever, ever going to write values for Pi and Hi because we just don't know how much is in there. Since this is a weak acid, we will always include as one of our inputs the value of Ka, which you can find on your formula page in that table. And in this case, it's 7.1 times 10 to the minus 4. And another input that we will always know for our acid-base problems is Kw, which is equal to 1.0 times 10 to the minus 14th. Next, let's look at our outputs. We're going to want to know what the concentration of X is at equilibrium, Y, P, and H. And once we find all of those, it is the concentration of P that will give us our answer. So look at that. We've got 4 unknowns, which means that we are going to need 4 equations. Our first equation, equation 1, is just going to be our equation for Ka, which we'll get from our first equation up here. Ka is equal to P times Y divided by X. equation 2 is just kW, which is just P times H. Next, we check to see if there are charged species in these equilibria, and there are, so our next equation is going to be a charge balance. So remember, on our left side of our equation, we add together all the positively charged species. It looks like those are H3O+, so we will have P equal to the sum of all the negatively charged species. So there's Y and H. For equation 4, we are going to need to do a mole balance. And for these mole balances, you have to be careful. You actually never want to do mole balances on acid-base reactions using either H or oxygen, just because they're present in water and it gets too complicated if you do that. So if you look at this entire equilibrium, the only other atom that is not hydrogen or oxygen is nitrogen. So that is the atom we're going to have to write our mole balance using. So all the nitrogen in these two equilibria are found in HNO2 and NO2 minus, and that is it. So accounting for those, we get equation 4 is equal to xi plus yi equals x plus y. We now have all 4 of our equations, and we are ready to plug into Mathematica. When you plug into Mathematica, it will eventually compute the value of P for you, which you will then have to convert to pH by taking the negative log of it, which you can also do in Mathematica. And that should be your final answer.